Hey, welcome back. Let's talk about our next topic today in thermochemistry. Let's talk about entropy, which is another factor that can affect the spontaneity of a reaction. So entropy is shown as the letter S. Now, entropy and enthalpy sound similar. The way that I might like to remember it is that enthalpy has a TH in it, which is why it's an H, and then entropy is just an S. So understand that entropy is a measurement of a degree of randomness or disorder in a system. Understand that the universe likes to progress towards disorder. So that means that most reactions spontaneously will become more disorganized, more random, naturally, without any sort of help. To go the opposite direction requires effort, but naturally, as far as the universe is concerned, it wants to trend towards disorder. So let's think about that by placing gases in a container. So let's say that I have two gases in a container. I have, let's say, gas X and gas O. In these other three containers, let's see if you can think of other ways that we can arrange X and O on both sides of the containers, right? Because imagine that you have two different containers. You know, one is one container, one's the other. They're connected by a tube. Let's think about the different ways that the gases can kind of pass around this tube. Let me show you what I mean. In other words, there's another situation where maybe the gases are all on the right. And then maybe there's another situation where the gases are separate like this. Or you could have the gases separate like that. Do you kind of see how the game works? So let's take this idea now, and let's see if we can think of ways that we can organize three gases. So let's say that we have gas X, we have gas O, and we have gas, well, let's not call it gas triangle. Let's be fancy. We'll call it gas delta. So I want you to take a second and see if you can figure out all the different ways that I can organize gas X, gas O, and gas delta. Pause, play around with a little bit. It's just playing with shapes. Come on back when you're done. All right, so these are all the ones that I came up with. Hopefully you came up with something similar. If you're in a different order than me, that's okay. But we first have all the gases on the right, and then we have X and O in one chamber and delta in the other, X and delta in one chamber, O in the other, and so on and so on and so on and so on. What you might notice here is that when I increase the number of particles, I increased what? What does this have to do with entropy? Well, I increased randomness. I increased the number of possible orientations for these particles to arrange themselves. I increased how random their position can be. Now, what if we do 4 particles? No, I'm just kidding. That'll take us too long. So, let's keep going. Understand that when we have changes in products in a chemical reaction, when we have them more disordered, this is a natural thing. So when we have a reaction, let me kind of restate that to make sure that we're all on the same page. When we have a reaction that trends towards disorder, this is what we would consider a natural process. This is, again, like I said at the beginning, this is like the way that kind of the universe wants to happen. So an easy way to analyze this is to think about your room. Think about it for a second. Maybe look around yourself if you're in your room while you're watching this. Do you have a clean room? Do you have a messy room? If you have a messy room, that's okay. Sometimes our rooms get a little messy. But think about this. What does it take for your room to get messy? It takes nothing. All it takes is for you to not do anything. And the next thing you know, clothes start piling up, things start getting dusty, your desk gets all disorganized, right? It doesn't take any effort for anything to get disorganized. That's just the way the universe do. Things trend toward entropy. What does it take for you to make your room clean? Well, it takes work. You have to get up, you gotta clean something, you gotta dust something, you gotta put things away. It takes consistent effort to keep your room clean. That's how this works in chemistry too. So we always trend towards disorder, but that doesn't mean it's always disorder. We can go the other way, it just takes work to do it. So this is the idea of entropy, and we can measure this mathematically, but in order to do that, we should probably understand what makes something disordered and what makes something ordered, right? Because remember, we are measuring disorganization, so like how messy something gets. That's what delta S measures, or excuse me, that's what S measures. So we can do some general predictions whether or not disorder is going to increase or decrease based on a couple of things. Let's say, for example, I'm given states of matter. Like I say that I have a solid block of ice, and that solid block of ice is becoming liquid water. Did entropy, go up, or did entropy go down? Well, let's think about this. Remember that entropy is the measurement of disorder. So that means solids are probably going to be the least disorganized because they're all uniform and stuck together. Liquids are a little more disorganized than solids. So that's supposed to be my greater than sign, but it's looking kind of bad. So solids are less disordered than liquids. Now gases are the most disordered out of all of them. Maybe I go at it from a different angle. That's a little better. There we go. So gases are more disordered than anything. So if I go from anything to a gas, it's immediately going to be an increase in entropy. It's going to be disordered. Now, aqueous solutions are kind of like right here. Meaning that if I go from solid to liquid to aqueous, that's an increase in disorder. Liquid to aqueous is an increase in disorder. And that's what we do for physical states. So what about temperature? So if I go from a high temperature to a low temperature, high temperature means the particles are all moving around, they're going all crazy. Low temperature means that everything's kind of slowing down. So that means a high temperature is going to have a greater disorder than a low temperature. Mixtures are pure substances. A mixture is just as a mixture of multiple things, whereas a pure substance is uniform throughout. So which one's more disorganized? Probably the mixture. So that means that a mixture is going to have higher entropy than a pure substance. Fewer particles or more particles? Well, the more particles I have, the crazier things get. I just saw that in the previous example. So that means that we are going to have a greater amount of entropy for more particles. Large molecules or small molecules? Well, large molecules are going to have a greater entropy than small molecules. So again, these are just general ideas. Like if I were to ask you, well, what do you think is happening to entropy going from solid to liquid? Well, you could say, well, entropy is increasing. But what does that mean? Well, we can quantify that, like I said. You can actually look in your book if you want. You actually are going to need your book because we're going to do a little practice here. But if you want to flip to your book on page 696, you can kind of see this. They have a couple diagrams here like gallium metal melting. Notice that the structures kind of break apart and they become a little bit more disorganized. So that's an increase in delta S. Evaporating, again, an increase in delta S. And dissolving is an increase in S. So let's look at these practice problems in the book, page 698. Now, please don't just mosey past these. Please try and work these out with me because they're really straightforward, but it really gives you an understanding of what it is we're trying to quantify here. No numbers yet, but let's just think about this on a conceptual level. Look here in the problem. It says, will the entropy change for each of the following be positive or negative? I'll show you one, and I want you to try out the other ones. So look at this first one. It says sugar dissolves in tea. So I have a solid block of sugar and tea, and now the sugar is breaking apart into the tea. Is that more disorganized or less disorganized? I would say it's more disorganized. So that means that I'm going to have an increase in entropy. So let's get a rule down here. So if S increases, then we have a positive delta S. So we're going to be measuring things in delta S. And I'm going to say if S decreases, meaning that I have a decrease in entropy, I'm going to have a negative delta S. So now take this idea and try and apply it to the other, 6 other ones, I think. And pause and come on back when you're done. Now hopefully you answered these and you have a clear understanding of why you gave the answer that you did, because entropy is really easy. It's just like, did it increase or did it decrease? But the important part of entropy is being able to explain your way through it. And if you're having a tough time explaining your way through it, look at the stuff above this, the predicting when entropy increases, because those are the why to what we're looking at. So let's look at it. B, frost forms on a window pane. We're going from frost to the window pane. That means we are going to have a decrease in entropy. Air is pumped into a tire. We have an increase in entropy because we are increasing the amount of particles in the tire. Increase in entropy. D, acetone evaporates from nail polish removers. That means we're going from a liquid acetone to a gaseous acetone. Anytime you go into a gas, it's always an increase in entropy because gases have the most disorder. All right, let's keep looking. Will the entropy change for each of the following be positive or negative? So these are a little trickier. They are chemical reactions. Notice that we have a solid calcium carbonate going into 2 particles. So there's a couple of things that you can point to here. You could say more particles, which means an increase in entropy. Or you could simply say the left has no gases, the right does have a gas, which means we are increasing the disorder because there's a gas. Now this doesn't really work for part B because everything's a gas, right? But again, now look at the number of particles. In the reactant side, I have 4 particles. In the product side, I only have 2. So that means I am decreasing in entropy. So again, explaining your way through entropy is the important part of this whole concept. But like I said, we can also calculate this. We can calculate entropy changes, which we would represent with delta S. And we calculate entropy changes in a very similar way than how we calculated enthalpy changes. So the formula is very similar. We have the entropy of the reaction is equal to the sum of the moles of the entropy of the products minus the sum moles of the entropy of the reactants. Meaning that we take the S values of the products, we multiply them by their moles, and we subtract that by the entropy values of the reactants. Now, the units for these are joules per mole Kelvin. Now, it's really important that you make note for yourself that this is in joules per mole Kelvin. Now, it's not that big of a deal right now, but it's going to be a big deal very soon. Please understand that this is joules per mole Kelvin. Why am I making such a big deal about this? Well, delta H was in kilojoules per mole Kelvin. So it might be a good idea to remember that they are in different units, or at least different magnitudes. Because let's say, for example, later, when I have to have those 2 values interact with each other, I'd probably want to make sure that they're the same. Just something to keep in mind. But for now, just understand that it is in joules per mole Kelvin. Now, let's look at an example. This is actually one that we did before, where we calculated the delta H for the 1 mole of methane gas combustion. This time I want you to calculate the delta S for the 1 mole of methane gas combustion. So you're going to use the same table that you used before, but now instead of looking at the H column, you're looking at the S column. I'm not going to do anything for you because technically you've already done quite a bit of this as far as writing the balanced equation and everything. You just got to go look in the book and find the values. Pause, come on back when you're finished. All right, so this should be it. Let's go ahead and make sure that we're all on the same page about what it is that I'm doing here. So all I did was take the values from each. So this is CO2. I just looked that up in the table. This is H2O. Notice that I have 2 H2Os, which is why I multiplied this by 2. This is CH4, again, just from the table. And this is O2. And one more time, notice that I have 2 O2s. So I want to multiply the delta S value by the 2. Because again, those values in the table, those are per 1 mole. If I have more moles than that, I have to make sure that I multiply those values by the appropriate number of moles. So when I do the whole thing, I notice that I get a value of negative 5.15 joules per mole Kelvin. Now, that's a pretty low number, which kind of makes sense, right? Because if I try to just guess, oh, you know, based on my trends, I'm going to have an increase or decrease, a lot of my rules kind of don't work, right? Because if I'm looking at it, they both have gases, they both have the same number of particles, so I can't really make any good assumptions, which is why I have to turn to the quantification. And in this case, I notice that the change in entropy isn't really that much, but it is a decrease in entropy just very slightly. So that is how you calculate delta S. And like I said, next time we might start interacting with delta H and delta S together to help us quantify and understand a thing called delta G, or in other words, Gibbs free energy. And that's it. I think that's entropy. We'll see you next time.